Is, I guess, Jessica Purcell who's talking about cusp volume of alternating knots, and I guess a slight change from her title in the sense her location is BYU and Monash University, so she's joining the Australian topology contingent. Thank you, Jessica.
All right, thank you. Well, thank you very much for the invitation to speak here. What a great conference. I found out yesterday at dinner, Francis is not 60. His birthday is September 9th. My birthday is September 22nd, which means he's a little bit older than I am. So I'm hoping that when I catch up to him, I will have proved as many nice theorems. Another thing I wanted to say, so Francis has excellent taste in mathematics, from a lot of knot theory results through the Kleinian groups to the quantum, some of the quantum things he's been doing recently. It's a very nice mathematics. Looking at the program, I seem to be the representative of the geometric knot theory for the conference, and that's fine. I'm happy to take that on. The work that I'm speaking about today is all joint with Marc Lackenby, and I've given talks on this work at conferences in 2 different continents. This is my first talk on the work in this continent. I didn't realize that there would be so many people from other continents who may have seen talks on this as well. So if you've seen me speak on this before, the introduction will be basically the same, but I'm going to try and give a little bit of a new emphasis after that. Okay. So, all right. So with that, let's begin. Okay. So the problem that I'm interested here is geometry of alternating knots. So particularly hyperbolic geometry. So here is a list of the first knots up to 7 crossings. And they're all alternating. So Manasco showed that the complement of any prime alternating knot except the 2 Q-torus knots are hyperbolic. So so that's that's most of the things on this list. I guess we have to exclude a few things. Let's see. So exclude the unknots, this one, and 7-1 here. And I think that's it. And the rest of those are hyperbolic. Okay. So what does it mean to be hyperbolic? Just a quick review of that. We're going to say that a knot is hyperbolic if its complement. So knots are going to be sitting in S3. So its complement in S3 minus K is going to be hyperbolic space quotiented out by a group. This group is isomorphic to the fundamental group of the complement, and it's going to be a discrete subgroup of PSL2C. So computationally, there are tools to compute hyperbolic structures on alternating knots. This was begun by Weeks with his program SnapP, which is now reincarnated due to Kohler and Dunfield, SnapP. And then Norman Thistlethwaite and Anastasia Sviatkova have an alternate program for alternating knots that will compute hyperbolic structures on those. So SnapP has led to a lot of open conjectures in knot theory. So here's an output of SnapP. So if I give it this knot, I can give it a diagram, and then I can tell it compute, and then it will give me a lot of information. And if I want to look at it visually, you click on a tab called Cusp information, Cusp neighborhood, and it'll give you a picture like this here in the bottom. Okay. So the problem that I'm going to talk about today arose from staring at these pictures in the cases of alternating knots and observing some similarities, some things that keep happening over and over again. So I'm going to start by defining a few terms to explain the problems we're looking at. Okay, so cusp. This is cusp volumes of alternating knots is the title of the talk. So let's define what a cusp is. So a cusp of a hyperbolic 3 manifold is an end, and this is going to be homomorphic to a torus cross 0 to infinity. Isometric to Horrell. I'll describe what that is. So in our setting, so we've got a knot. So let me draw a picture of that. So here's a knot. And we're looking at, remember, we're looking at the manifold S3 minus K. And so a Horobal neighborhood is going to be, essentially it's going to be a geometric neighborhood of the knot. So if you take a little tube around the knot everywhere, this is going to connect up to give you a torus. And when you take the thickened neighborhood of this, this is going to be a torus cross 0 to infinity. We're going to include the boundary of our tube, but then you can't go all the way out to infinity because it doesn't exist. Okay, so that's our setting. And then a Horobal, okay, so we're going to be working with the upper half space model of hyperbolic 3 space. So upper half space model, as we all know, this is, we consider the points x, y, z such that z is greater than 0. And a Horobal about infinity is just a plane, horizontal plane, in this case where we're gonna pick z, right, z greater than or equal to c, where c is some constant. Okay? So now recall we have this subgroup gamma, which looks like the fundamental group of my knot complement. And there's a subgroup of that in PSLTC that fixes the point at infinity. So we're going to call that gamma infinity. And what this is going to do is it's going to be translation in a couple of directions along the horosphere. So if you quotient out by this group, gamma infinity, then what you end up with is a Euclidean torus on the boundary of H3 infinity. I guess that's kind of true. What I really meant is on the boundary of a Horobal. Okay? So this Euclidean torus is what is called the cusp, or the cusp shape. All right, so I put this on the top of the next slide. All right, so the cusp shape, right? So we have this Euclidean torus on the boundary of our Horobal. And if you take, okay, so now take an element gamma, which does not fix the point at infinity. And if we apply this to the Horobal, so here was our Horobal at infinity in hyperbolic 3 space. So here's H. Gamma is going to take the point at infinity to some other point on the boundary of hyperbolic 3 space. And it's going to take the Horobal to some ball tangent to that. Okay? And so this is what the picture was that we were looking at in SnapHeat. So let me go back a little bit to that. So in this picture, your head is sitting at infinity, and you are looking down into your Horobal. So you're in a Horobal neighborhood. This purple rectangle is the cusp shape, is the cusp neighborhood. So that's the Euclidean torus. And then all of these circles that you see, these spheres, these are Horobals, which are the images of the Horobal of infinity under elements of the fundamental group. Yes?
Is that a rectangle? Are those right angles?
Those are right angles in this case, yeah. That doesn't always happen. All right, so if you grow the Horobal a little bit, so expand this one out at infinity a little bit, that's going to make this one here grow a little bit too. Kind of hard to draw. So you can grow and shrink the Horobals, and there's going to be a point you can grow them up until they become tangent, and that's going to be the largest embedded cusp. So this is defined to be the maximal cusp, the largest embedded choice. We're going to call the particular Horobal H infinity in that case. And for a knot complement, if you have a single cusp, then that's well defined. All right, so once you have a maximal cusp, then we can define the cusp volume and the cusp area. The cusp volume is the volume of the maximal cusp, and the cusp area is 2 times the cusp volume. I think off and off by a factor of 2 there. I think it's 2 times the cusp volume. Okay, that's an exercise in hyperbolic geometry. All right. So this is a Horobal. This is supposed to be a 3D. So if you have a Horobal sitting on the plane at infinity, then you can draw a line, a straight line, from this point where it's tangent up to the point at infinity. And this is going to be a geodesic in hyperbolic 3 space. So in between these two horoballs, we have an arc here that is embedded in the 3 manifold, the knot complement. And so what is that? Well, it runs from a point at infinity that's inside, right? It's this dotted line here is inside my tubular neighborhood about the knot. This dotted line up here is in the, you can't see that. This dotted line up here is inside the tubular neighborhood about the knot. And so this blue geodesic is going to be an arc that starts somewhere on the cusp and does something, and then comes back. Okay, the question is, where is this arc? So where is it? So this seems to be a somewhat difficult question to predict in general, given a collection of horoballs versus a topological description, the diagram of a knot. How do they talk to each other? Where are the geodesics? What are the, in terms of the topological description, this combinatorial picture, what is the isotopy class of that geodesic over in the diagram? So Mormon Thistlethwaite, he observed that for alternating knots, the sequence of large horoballs on the cusp neighborhood seems to correspond to a sequence of crossing arcs. So what is a crossing arc? A crossing arc is about the simplest arc that you can draw in the diagram. So that is, it's just an arc that goes from an overcrossing to an undercrossing. So if this is a crossing of your knot, a crossing arc starts here, goes down to there. Okay, so in this diagram here, here's an example of a crossing arc. All right, so let me show you by this example that I had what this looks like. Okay. So I'm going to start on my knot right here. And if I'm walking along the knot, then I will be passing crossings. So if I'm going to start and I'm going to go in this direction. And when I get right here, I'm at the bottom of an undercrossing. And so thinking of myself as walking along a horoball at infinity, I am going to see a crossing arc going off somewhere. And I want to figure out what that is. So here's my first crossing arc. Let's call that 1. And then over here in my picture of my horoball, I'm going to just circle this ball right here, and I'm going to label that with a 1. Okay, so I continue walking this way, and I'm going to see another crossing arc right here. But I'm not going to do anything with that one because it turns out that this first one that I cross is homotopic to this next one right here. So this is still a 1. So I'm going to just keep the label on this horoball over here, the 1, and continue walking. Okay. So I carry on. I get over to here, and here's my next crossing. So let's call this 2. So I'm going to label that guy 2, and there's the same one. Those are both 2s. And then carry on. Here's a 3. Let's label that 3. Here is a 4. Let's label this guy 4. There's another 4 up there. And again, if I keep going, this 4 is homotopic to this arc over here, so I'm going to skip that one. And I get a 5 over here. That's just a little guy. Let's label him. And then I'm back to 2. So I label this with a 2. And I notice that that's about the same size as my other 2. That's good news. All right, so let's see, where am I? I need a new one. So here's 6. 6 is small again. And then I'm back to 4, which was big, and it still looks big. And then I'm back to 1, which also looks big. And then I go to 5, to 3, to 6, and then I am back where I started. Okay, so Thistlethwaite was drawing lots of pictures on alternating cusp diagrams and seeing that this choice of large horoballs seemed to match up very well with the choices of with the sequence of crossing arcs that you pass as you are walking along the cusp of the diagram. Okay, so this is what he observed. And he made a conjecture. So his conjecture, he didn't write this down anywhere, but I've seen it in a few places. He conjectured that in an alternating knot, these large horriballs correspond to crossing arcs. Or to put this more precisely and more formally, he conjectured that in a reduced diagram of an alternating knot, the length of a crossing arc measured outside of the maximal cusp is at most log 8. So he conjectures that there's this universal bound of log 8 on the length of any crossing arc. So notice, this is kind of key, this is important. The length of the crossing arc, if the length is short, so the length is bounded by log 8, that means that this horoball has to have large diameter, right? So short geodesic here implies a large diameter horoball. All right. Okay. So this is a very interesting, intriguing conjecture that I don't know how to prove. But I do know how to prove a slightly weaker version of this conjecture. So let me give a little bit more terminology, and then I can tell you what we were able to prove. Okay, so first term we need to talk about is a twist region.
Wait, I'm sorry.
Yes.
Could you just state his conjecture again, or on
Yes.
Okay,
So his conjecture is that in a reduced diagram of an alternating knot, hyperbolic alternating knot, I should say here too. That's kind of key, right? Hyperbolic. The length of a crossing arc is universally bounded, and namely it's bounded by this number log 8 that he has.
And I guess I want to ask where the 8 came from. Is that just from data, or?
I think that just came from data. Yeah, I think the 8 came from data. It came from Anastasia Sviatkova. She told me that's what he conjectured. So.
Natural logarithm?
What's that?
Natural logarithm?
Yes, natural logarithm. Okay, so a twist region of a knot diagram is a region in which two strands twist maximally. So let me just draw a picture of that. What that means is in the diagram you're going to have a sequence of bigons, and they're all connected by crossings. So this is what a twist region looks like. And it's maximal in the sense that you include all of the crossings, right? You don't leave somebody off over here. So this is the whole twist region. And you can see pretty quickly that alternating is important. We're only dealing with alternating knots anyway, but if it's not alternating, then you can simplify the diagram a little bit, remove some crossings. So we're not going to worry about non-alternating things. Okay, there are other ways. So we're going to want to count the number of twist regions. And so we want to make our count intelligent. So for example, we don't want to count something like this as a twist region, because why? What can we do with that? Yeah, we can just undo it and it goes away. Okay, so if the diagram is prime and twist reduced, then we'll be counting the correct number of things. So a diagram with this sort of a thing in it, this is not prime. Okay, so more carefully, it's going to be prime if any simple closed curve that meets the knot twice does not bound crossings on one side. Okay, so and then twist reduced is kind of a similar notion. If you have a twist region over here, and then these strands go into some sort of a box, and the knot does something, and then it comes out, and then there's another crossing on this side, you can take that whole box, and you can twist it around, and you can undo that crossing, and you can move it to the other side. Okay, so the way that it's drawn here, if this question mark is not diagram, then you would count this as two different twist regions. We don't want to do that. So twist reduced means you have done all these flights to put all of the twists into a single place. So it's twist reduced. Twist reduced implies that this question mark box is just a continued portion of the same twist. So a bunch of bigons like so. Okay, so once we have this out of the way, so when you have a reduced diagram, then you can count the number of twist regions in the diagram, and this is called the twist number, and we're going to denote it by twist of k. All right, and then an observation is that two crossing arcs in the same twist region are always going to be homotopic.
So is it always possible to twist reduce a diagram?
Yes, it's always possible to twist reduce a diagram, yes. Yeah, just by the sequence of moves.
So it terminates.
Yes, yes. Okay, so here's the weaker conjecture that follows from this conjecture of Thistlethwaite. The conjecture is that the Cusp volume of an alternating knot is bounded linearly in terms of the twist number of a reduced alternating diagram. So in other words, there are constants A1, A2, C1, C2, such that A1 times the twist number plus A2 is less than or equal to the cusp area of K, which is less than or equal to C1 times the twist number plus C2. And it is a fact that the strong conjecture, so remember the strong conjecture, this says that all of my crossing arcs have length less than or equal to log 8. Well, this is certainly going to imply the weaker conjecture, because every crossing arc, so how's that going to work? Every crossing arc is going to give you this big Horowall. The big Horowall is going to have a big shadow on the cusp. And so this is going to contribute to area. You're going to get a lot of embedded circles like this that are going to give you a lot of cusp area. And how many? Well, you're going to have, for every crossing arc, that is, in every twist region, you're going to get a new one. So your area is going to be about the twist number. Okay? All right.
Is that a minus sign on the A2?
It doesn't matter. Make your constant negative if you like. Okay, so here's what we can prove. So here's our main result. So this is with Marc Lackenby. We prove that there exists a constant, A, such that A times the twist number is less than or equal to the cusp area is less than 10 root 3 times twist minus what? So notes on this. The upper bound is not new. This is well known. So the upper bound is due to Marc Lackenby proved that the volume of the entire knot complement is bounded in terms of the twist number. This was improved by Agel and Dylan Thurston. And then to turn that into a result on cusp area, you can use some packing arguments by Borowski that tell you what the cusp area would be. Okay, so there's the upper bound. The lower bound, so the lower bound is the exciting part. We're quite excited about that. Not only do we have a bound, but we can make it explicit. So that means that if you want to prove something about, in terms of cusp areas, then you can take our number and you can exclude everything with at least a large number of twist regions determined by A, and then run the rest of them, the smaller cases, you can maybe deal with by computer. Well, in theory, in practice, it'll take you a long time because our value of A is kind of small, but it's explicit. So.
And it's positive.
And it's positive. That's true. There was a known, a known lower bound. Okay. All right. So I'm going to talk now. Oh, a little bit about related work. Okay. So actually, in some of my thesis work, I proved similar results on cusp shape for what I call highly twisted knots. So highly twisted knots, so this was a nice step along the way too, but highly twisted knots are knots that have twist regions, but in every twist region, so remember twist region is where you have a bunch of crossings, like so, as long as you have at least 145 crossings per twist region, then I had a lower bound in that case. With David Feuder and Effie Calvagiani, we gave a proof for two-bridge knots, and I didn't write down the constants, but they were much nicer. They were, right? You remember? You don't know off the top of your head.
But it was bigger than one.
Yeah. Okay. And then I should also say, so Anastasia Svietkova and Morwen Thistlethwaite, with their program, they computed thousands and thousands of examples, and they had examples of this. They had computer evidence. that this was the case. Okay, so let me talk about a couple of applications really quick before we jump into the proof of this. The first application I want to talk about is kind of an interesting geometric consequence of this. So if you define the cusp density of a knot to be the area, the cusp area divided by its volume, then for alternating knots, there is a universal lower bound on the cusp density. So this is unusual. So Mario Udave Munoz and John Lukey have found examples. I think they were the first. There are lots and lots of examples of these things now, but so I think the first examples were due to these two. They found examples of knots whose cusp density became as small as you want. So given any epsilon, there exists a knot with cusp density less than epsilon. So that's not true in the case of alternating knots. Just really quickly, maybe let me write down an idea of how the proof of this goes. So what you're going to use, I mentioned this before, there's a bound on volume due to Lackenby, Agel, Dillon, Thurston. They showed that the volume of an alternating knot, in fact the volume of any knot, is less than or equal to 10 times, this is the volume of a regular ideal tetrahedron, that's usually called V3, times the twist number. Okay? And so this means that the cusp density is going to be bigger than or equal to, so from our result we've got this constant A times the twist number over 10 V3 times twist minus 1, and you can see that this should be bigger than or equal to A over 10 V3, because twist over twist minus 1 should be bigger than 1. I think that works. Okay, so there you go. So that's a quick proof, or a quick application. So alternating knots are unusual. So another application is topological, which also shows that these are somewhat unusual. So this one relates to Dane filling. A corollary is that if you take a closed orientable 3-manifold that has a sufficiently large Gromov norm, you can think of that as volume if you're more comfortable with that. Then what? Well, then there are most finitely many prime alternating knots and finitely many fractions P over Q, so the M is obtained by P over Q surgery along K. So this was an open problem whether whether this sort of statement was true in general. Osoynak, I don't know how to pronounce that name, he proved that this is also false for general knots. So there do exist closed orientable 3-manifolds which are obtained by Dane surgery along infinitely many knots in S3. But so what this shows is this, at least if your volume is big enough, this is not going to happen for alternating knots. Okay, so I think I'm going to skip ahead and let's talk about the proof a little bit. All right, so here's an idea of how it goes, and I'll go through some of these steps a little bit more. So our theorem was, just a reminder, there exists a constant such that A times the twist number is less than or equal to the cusp area. Okay, so what we're going to be looking at is we're going to be looking at cusped essential surfaces sitting inside of S3 minus K. So the first step in our proof will be to find such a surface. And then our second step is to show that the surface contains, so we take it down a dimension. So rather than working in the 3-dimensional knot, we're going to look at a surface, and we're going to show that this surface contains a large number of essential arcs that all have bounded length. Here we can use some sort of explicit constant to find this. So our large number is going to be roughly the twist number. And then we're going to map the surface back into the 3-manifold. So we start in 3D, we go to 2D, we find arcs, we map the arcs back, and each one of these arcs is going to stay bounded length. The problem is some of them are going to land on top of each other, and so we're not going to get as many as we started with, but if we control overcounting, then we'll be okay. Okay, so let me say, all right, so another main result that we're going to need is what I call this surface theorem. And this is going to give me a large number of arcs of bounded length inside of a surface, all right? So if F is a finite area hyperbolic surface with cusps, sorry, there's a little typo here. And h of F is an embedded Horoball neighborhood of the cusps. Then what? Take K, oh sorry, this is another typo. Take K to be the area of the cusps divided by the area of the surface, and you can pick any number D that you want. Then you can do a calculation and find that there are, all of this is computed in D and K, here's some function, times the Euler characteristic of the surface. There are this many geodesic arcs with length at most 2D. Okay, so morally what this is saying is we get a large number of arcs of length bounded by 2 times D, where D is our favorite constant that we want. Okay? Okay, so I wanted to go through really quickly just the proof idea of the surface theorem. So it looks a little bit complicated, this equation in terms of K and D and cinches and 2 pi's and whatever. The idea though is actually quite simple and straightforward. So if we're going to let G be the collection of arcs of bounded lengths. So we're going to take G to be arcs of length less than or equal to 2D. Okay? And we're going to lift those to the universal cover, which is hyperbolic 2 space now for dimension 2. And what we're going to get, so my surface lifts to, my HF, remember HF was my Horoball. And it's going to lift to a Horoball about infinity, I'll just call it HF again, and then other Horoballs elsewhere, maybe some big ones and some small ones and so on and so on. And if I have an arc in here, so say G and G prime, then these are going to lift to give me arcs in the universal cover that have bounded length. So here's, I should have made that dotted, but anyway, here's, say this is G prime, and they have bounded length. Okay, take an interval about each of these arcs. Whoops, where did my line go? Okay, take an interval of length 2 pi around each of these arcs. That's where one of the pi's came from in the previous theorem. And we're going to keep everything fixed outside of these intervals, but away from the interval, I'm going to extend my horosphere down, distance d. Okay? So when I do this, I pick up a piecewise horosphere. Piecewise horosphere. And because of the choice of these the length of 2 pi, the arcs have length less than or equal to 2d, it turns out that this guy, let's call him P for piecewise, this is going to be embedded. Or rather, when I take its image, we project back down to the surface, this is going to be embedded in F. So image of P is embedded inside the surface F. Well, what does that mean? That means that the area of F is bigger than or equal to the area of P. And the area of P is just the area of my original horosphere plus these extra chunks depending on the length of my original interval. And so from there, you're going to use an Euler characteristic argument to tell you how big you must have been in the first place. Okay. So another way of saying this, if you argue by contradiction, if there aren't very many long arcs, you're going to get big, wide regions where you have piecewise horosphere. Those are going to pick up lots and lots of area, and that's going to be more area than you have to play with to begin with. So there's going to be more area than you have. So that's the idea of the argument, just these piecewise foresters. Okay, so once we have this surface theorem, we can use this to prove the Cusp volume theorem. So we're going to find an essential surface in our manifold, and it's going to have area some constant times the twist number. So area roughly the twist number. The fact that this is essential means it's going to inherit a hyperbolic structure from the structure on S3 minus K. The surface theorem is going to tell me I have about twist of K number of bounded length arcs in the surface. I'm going to map them back into my knot, and I'm going to straighten them. The length is going to stay bounded. So the arc is going to correspond to a large four-ball, which is going to contribute to the area, as we've seen. The shadow, kind of, dot, dot, dot. Unless we have multiple distinct arcs that are homotopic. So let me give you an example of where this is going to come up. We'll see this again, but let me just draw a picture here quickly. So for example, if my surface happens to be something like this around my knot. Okay, so in the knot, there are these twists. In the surface, what is that? Well, that just means that we've got this bit of a puncture, but we've got surface that goes, it's like a handle, right? We can send an arc down. Maybe I should do that in a different color. See if that switched. Okay, yeah, so we can send an arc down there. Here's another arc in the surface that's essential. We can send an arc like that. These two arcs have nothing to do with each other in the surface. They don't talk to each other at all. They're totally disjoint. But when you map them back into the knot complement, they're both isotopic to crossing arcs, and in fact, they're homotopic to each other just by sliding along the bygone areas here. Okay, so you do have to worry about multiple distinct arcs mapping to the same place. Okay, so we have to control overcounting is kind of an important step that made this more complicated than it would have otherwise been. All right, so what surfaces are we going to use? My last slide was a hint of this. We have, let's go back to black. We have to deal with two cases. So the first case is simpler. If we have only at most n crossings per twist region, so n is going to be some number that we're going to pick later. If there are less than or equal to n crossings per twist region, we're just going to use the checkerboard surfaces. So checkerboard surfaces of knot complements are super nice. We know a lot about these. There are two of them. They're red and blue. So here's one. You just fill in all of every other region, right? And then you connect these regions by twists. So I shouldn't have chosen the one with the unbounded region. It's harder, more to shade. But okay, and so then there's the other one that's white, but right. So that between these regions, you just put in a little half twist, and they meet up. Okay, so we know that we already know that these are essential. So there's no extra work to do there. So that's great. If we take the union of the two of them, so we're going to let F be the we can think of it as a disjoint union if you want things to be nicely embedded. Well, they overlap at crossing arcs only. So take your surface F to be our union B. Then the area of this thing is just 2 pi times the crossing number minus 2. There's actually, so there's a quick reason that that's true. Let me draw you a quick proof. So inside, here is a zoomed in one crossing on the knot. The checkerboard surfaces, you're going to have the two of them, right? So one of them is going to run like so. That should go under and then up and around. And then it connects on this side. So you have red this way, and then you've got blue. Connecting underneath, and then it goes around to here. And over here it's on top, and then it goes underneath and connects up like so. Okay, if you stare at this long enough, there's a rectangle that goes over the crossings. So it starts at the crossing up at the top, and it's got a corner up there, it's got a corner down here at the crossing at the bottom, and then in the middle, the rectangle goes around the knot, and its two corners are identified to the same point. But if you look at, so this is going to be true for every crossing. Basically, this means that there's a little hole above every crossing, and otherwise you filled out the entire projection plane, which is a sphere. So what have you got? You've got a sphere with C of k holes. This is just the Euler characteristic of a sphere with C of k punctures. Okay, so that's one way to see that, is to notice you've got a rectangle hole for every puncture. All right, so the surface theorem then tells us that we've got at least some constant, this can be computed explicitly, times the crossing number minus 2, short geodesics. Okay, let me see, was there anything else I wanted to say about that? Okay, overcounting, right. So, sorry, we lost my picture, but overcounting, we need to worry about distinct arcs that are going to be homotopic. We saw in this picture before that crossing arcs that are in the same twist region are all going to become homotopic. So we can't count those, but it turns out that we were able to show that any two distinct arcs in the checkerboard surfaces are going to be homotopic if and only if they lie in the neighborhood of the twist region. So in fact, that means there are going to be at most 3n minus 1 repetitions. And so you can take the area, you get the number of arcs depending on the crossing number, but then you divide out by 3n minus 1, and this is going to give you a universal upper bound, provided your n is not too big. So if you have a finite value of n, that this will work. But notice that if n begins to grow, then this is not going to be helpful, because we're going to be dividing out by something that's getting bigger and bigger and bigger. So in fact, the checkerboard surfaces are very, very, very nice for alternating knots, and lots of great things have been done with them, but they really aren't showing the geometry appropriately. So when you put in a lot of twist regions into a knot diagram, the checkerboard surfaces are getting more and more complicated. They get a handle for every crossing in this twist region. But in terms of the geometry, putting more and more twists into this is approaching a geometric limit. So the geometry should be stabilizing. So we had to deal with this phenomenon. So the checkerboard surfaces are not really the geometric thing that we wanted to use, to say something else. So in the case of high twists, we had to deal with slightly different surfaces. So if there exist twist regions with more than n crossings, then what we did were we took these things that we call twisted checkerboard surfaces. So here's the idea. Here's a picture of what this looks like. So let me see what it goes. So if you've got a region with a high number of crossings, say 145, for example, that's pretty high, then what we're going to do is we are going to drill a curve out of that. So here's my twist region. We're just going to take a simple unknot, like so, call that C, and we're going to drill C out of the knot. So this is going to give me a totally different manifold. This will be a link complement still, but it's not at all homeomorphic to what I began with. We've got too many boundary components. All right, but a nice thing about this is this is going to be homeomorphic to something where I can remove basically all pairs, I can remove pairs of crossings. There's a homeomorphism, taking this to a guy with all, let's see, any choice of 2R crossings removed. That is from this twist region, from twist region. Okay, and it works out for purposes of the results that we needed. It works out best if we leave 1 or 2 crossings here.
What's the intuition behind why you don't want to leave 0?
We need to have a little bit of cusp area coming from this particular twist region. If there is 0, then we're not going to see. We get cusp area. Well, here, that's a good question. Let me just zoom back really quick to this picture. It looks like a mess now that I look at it. We get cusp area by going over a crossing. And so we need to keep crossings in order to pick up that area. So that's the reason we need to leave 1 or 2 crossings. Okay, so leave 1 or 2 crossings, and this will give us a new link, and this link is going to be nice, and we're going to work with it, but it's related to the first one by a Dane filling. So if you do a 1 over r Dane filling, remember here, if I remove 2 r crossings, then a 1 over r Dane filling is going to take me back to exactly the not complement that I began with in the first place. Okay, so the surfaces that I'm going to take come from the checkerboard surfaces. Let me switch colors again. Checkerboard surfaces over here. So I'm going to take the checkerboard surfaces of this guy. So which guy? So let's call the knot here, let's call that K2. And then we've also got these crossing circles, C. So the link is K2 union C. The knot is K2. We take the checkerboard surfaces of the knot, and then we pop holes in them. So we puncture them by these little meridians where it meets these links, these C links. Okay, so surface with holes popped for the punctures. And this is going to be my starting surface. Okay, so we're going to have surfaces R and B, and these come from checkerboard surfaces. Checkerboard surfaces of K2 with holes from these links C. All right, so this is a surface inside of a link complement, not inside of my not complement. I need to get back to my not complement. So what do I do? Okay, so here's a picture of what I do. Start over here on this side. So my surface looks something like this. It meets the guy in meridians. All right, I probably don't want to shade that. It's harder to see. This link is an unknot sitting inside of S3, which is made up of the union of 2 solid tori. If I take my head and I move it inside of C, then I'm going to see my knot sitting inside of a solid torus like this. So the dotted line here, the dotted line here on the left is the same as the dotted line here in the middle. So the knot is sitting inside of here, right? So this is C. And now it's pretty easy to see what's going on if you twist this up again. If you put back the crossings, then this meridian curve, this blue, let's go back to blue, this blue curve becomes a longitude like so. And when we slice and twist, what happens? It gets twisted however many times, and then move your head back on the outside, and you've got a negative 1 over r curve, I think, in this case. Okay, so this is sitting inside of, now this is the knot with crossing circles added. So we still have to get rid of those crossing circles to go back to the knot, only now it's just simple meridian Dane filling. So we're just going to put a solid torus in here. What's going to happen to the surface? Well, that's this next line down. My surface, here's like a negative 1 over r curve here. If I take a little cross section of that, that's the middle guy. Cross section, we're going to see a bunch of parallel curves, and there's going to be an even number. And we find the guy exactly opposite, and we just connect, like so. So we're going to attach an I bundle. Okay, so there aren't very many I bundles over a circle. We're either going to be attaching an annulus, or we're going to be attaching 2 Mobius bands in every case, and we're going to end up with the twisted checkerboard surface. Okay, so that's how you construct it. All right, so the properties of this twisted checkerboard surfaces. So we get 2 surfaces. There's a red one and there's a blue one. And these are immersed. However, they are embedded everywhere. The immersion comes, you've got these super high crossing regions, and they're doing something. The immersion comes around the remnants of the crossing circle. So if we don't drill it out, but we put it back in, the surface is going to be intersecting itself only on these curves corresponding to these crossing circles. Okay. Okay, so then the hard part, this actually ended up being quite a hard theorem. We had to prove that these were essential. So provided that, remember we define these by choosing, saying put in a crossing circle if n is bigger than something. Provided n is greater than or equal to 33, we were able to prove that these are both essential surfaces. Okay, and that the proof was combinatorial in nature. It used very heavily the fact that these were alternating diagrams to start with. But I think there may be ways to generalize that to other surfaces as well. So that could be useful. Also, I'm shopping for a new proof. If you have a better one, this was kind of tedious. So keep that in mind. Okay, Euler characteristic. We want to know how many arcs are we going to get out of these? Well, the Euler characteristic of these surfaces is the number of remaining crossings. This is what I mean. These are the crossings. Remember, we have the knot K2. So you remove pairs of crossings in these high crossing twist regions. There's going to be some knot K2 left over. We're going to take the crossings coming from that knot. And remember, so the reason why is because we just had these are just checkerboard surfaces for K2 to begin with. And so we know that the Euler characteristic for that was C of K2 minus 2. This is the Euler, right. Sums of the Euler characteristics of the checkerboard surfaces of K2. Because this is a K2 punctured sphere. Okay, then what is this? So now you take all of the things that have at least, this notation here means, look at the twist regions with at least n twists in them. And we're taking this surface, these checkerboard surfaces, and remember we punctured a hole, and we actually punctured two of them, once on either side when we put in this this crossing circle. And so we lose, what that does to the Euler characteristic is you lose the 2 times the number of twists where we put in these crossing circles. So these are from the punctures.
So n is a parameter that you'd like just to be smaller? Or?
Yeah, we would like to make n as small as we can, but it's got to be at least bigger than 33 for these to be essential.
If your diagram had no twist regions with more than 33,
then these turn out to be exactly the checkerboard surfaces if they're, if n is big enough. That's right.
Then you win. Okay.
And then we win. Yes. Well, we still win.
You win, yeah.
That maybe a bigger constant. Right. Okay, and so we added these. So we added these punctures, and then remember the last step is you attach the annulus or the Mobius band. Well, attaching annulus or Mobius band has no effect on the Euler characteristic. So that's a quick proof that the Euler characteristic is what we want it to be. Okay, and now we have to worry about overcounting. And so unfortunately, n has to go up a little bit more. If it's bigger than 39, then it turns out that there are at least 6n minus 4 distinct arcs. Or, sorry, at most 6n minus 4 distinct arcs, which are homotopic in S3 minus 8, right? We want to bound the number of arcs that map to the same place. They all are going to live in the same twist region, is what we can prove. But if in this case you can get at most 2 times 3n minus 2. Okay. I think those are all my properties. They are. Okay, so now, all right, so this is a quick slide, so I probably should have broken this up. But, all right, now we're ready to assemble the entire proof. Okay, so we're going to let n be greater than, we're not even going to take greater than or equal to 39. And form the twisted surfaces R and T. So in other words, if you've got more than 39 crossings in a twist region, put in this little link, undo, take the checkerboard surfaces, twist up again, and there you go. You've got these surfaces R and B. So the surface theorem, when you put in your constants, K and D, then this will imply that there are at least yay many. So Euler characteristic of R plus Euler characteristic of B divided by 9,511. So there are this many arcs whose length is at least, or sorry, at most, keep my inequalities going the right way. So at most 2 times this constant. We picked this one because it worked out nicely. but our constant is, essentially it's about 2 times log of 76 pi. Okay, and then back to that estimate from the last slide, we have 2 times 3 times n, this is n, here's n, minus 2 is 230 homotopic arcs. We have to divide by that number. So putting it all together, the cusp area is, so from this term comes from the surface theorem. This comes from controlling over counting. And then this is going to measure the shadows, right? So to get the area, remember we have these short arcs, we have to measure areas of their shadows. So areas of shadows are giving me cusp area. This is over counting. And this is from the surface theorem. Okay, so that's not too bad. So the pieces individually are fine. And then you do a little bit of multiplication. And there we go. So the cusp area is at least 2.436 times 10 to the negative 16 times twist number minus 2. So I will stop there.
So questions or comments?
Could you explain this application to the Gromov norm a bit more?
Yeah, I can. Let's see. I'll see if I can find it. Whoops, too far. Okay, so this theorem, I assume. So yeah, so if you have a big enough manifold, what this says is there are going to be at most finitely many alternating knots that are going to give you, and finitely many surgeries that are going to give you this manifold when you do P over Q surgery. This follows from a couple of different pieces. So maybe I'll just say in words. So Darrell Cooper and Marc Lackenby proved a few years ago that if you have a slope with length at least 2 pi plus epsilon, then there are finitely many manifolds obtained by Dane filling that particular slope. Okay, so if the Gromov norm is large, on the other hand, so let me write this down. So the first piece of this is Cooper-Lackenby. And the second piece, if the Gromov norm is large, then this implies that the volume is large of the original knot. And then Lackenby, Agel, Gill, and Thurston implies that the twist number is large. Okay, and so then our theorem implies that the slope length is long. And so that's what gives the result, basically. Okay, so these guys, these needed the 2 pi plus epsilon. If the Gromov norm is large, then the volume is big, then the twist number is big, then the slope length is big. And so therefore, you only get finitely many Dane fillings. Yeah, that's the way that
went. So when the equality will be achieved in your result?
So, I'm sorry?
The lower bound is bigger or equal, so when the equality will be achieved?
Oh, when will equality be achieved? Hopefully never. So hopefully our bound is terrible, and Thistlethwaite's conjecture is better. So Thistlethwaite conjectured log 8 was the length of the geodesics. If you plug that in, then the lower bound should be about, let's see, I did the number. I think it's 0.6. Yeah, instead of 2 point something times 10 to the negative 16, it should just be 0.6. But even that, I don't think it should ever be obtained. Because if that would be the case that all of the geodesics have length bigger than log 8, which would mean all of your horaballs were small, but that never happens. You have big ones as well as small ones. So probably the lower bound will never be obtained. Yeah, so that's a good question.
If there are no other questions, thank you very much.